Hey everybody.
Hi.
How you doing, Sam?
Pretty good. How are you doing?
Pretty good. I think we got a pretty good crowd tonight. All right, so welcome to RocPy. And Sam is going to be talking about machine learning techniques. And George has the recording going. So, anybody want to, any announcements, or anybody want to get anybody's attention before we get going? Where's the chat? Oh, okay. Well, if anyone has anything that they want to contribute or ask while we're going through, feel free to pop on the video and or the chat and or voice, and we're open to as much interaction as you're interested in participating. So with that, Sam, take it away.
Okay, so I just have a small project that I put together over the past few days that I'd like to just demonstrate here, and then I can talk about the Python that went into it. It's a self-driving car type of thing, where a bunch of AI agents, they attempt to drive towards a point that's moving around in a circle, and it uses a neural network and genetic algorithm hybrid type of algorithm to do that, which I'll go over. And it's available on GitHub. I'll show the link for that after pretty close to the end of the presentation. So how do I share my screen here? Can I just...
There should be a share screen icon, that little green icon with a box with an arrow in it right in the middle of the bottom of the window. There you go.
Can you tell me what you're seeing right now?
Agent.py, and
okay.
Good.
Yeah. All right, so it looks like that right screen is sharing. So I guess we can jump into this then. This is what it looks like, the final product. You can see the cars at the beginning, they have no idea what they're doing. They're all driving towards the wall. And then I move on to the next generation. They're a little better. They're supposed to be tracking that black dot that's moving around in a circle. And you can see they're kind of steering towards it right now. And this time they'll be a little better. The idea is that every successive generation is going to be better at tracking the car, or at tracking the dot. But there's no explicit code written anywhere for these cards to track this dot. It's learned on its own. And the reason like this, why it might get worse sometimes, is because there's a mutation factor going on. I'll explain all that later. But sometimes the mutation makes it worse, which is obviously not a desirable outcome, but I have a pretty high mutation rate on this, so it's not completely impossible for that to happen. Although in the long run, it will always get better. It will always trend towards the best solution. So each of these agents, they're called agents. The cars, they're called agents. That's just a machine learning term. But this file right here is the main file that just runs the program. It's using the Pygame library to draw everything to the screen. But just this thing right here, I don't know what I just did. But this block right here is the game loop, or the update loop. And this is where everything is controlled. So just to go from this line by line pretty much, because this is not much. So this clears the screen so it can draw the next frame. It updates the position of the black dot to move in a circle. It changes the angle of the black dot, updates the entire generation, the entire group of agents. That I call it the species. And I'll go over that class later. This is the species class, which contains all the agents. It draws a circle where the target is, or where the black dot is. It updates the screen and keeps the frame rate at 30 frames per second. Then it checks the event loop. That's what this is. It checks if the user closes out the screen or presses space to do the next generation of agents. So the actual machine learning of this in the agent class, which is the class for the movers, the cars, the machine learning part of this is shown right here, where it says self.brain equals neural brain, and it passes some arguments to that. The neural brain class is the actual machine learning algorithm implementation, at least the neural network part of this, which is over here. So to understand what this is doing, I kind of made a little diagram here. I don't know if it's hard to see. I just kind of made this. So, but I wonder if there's a way to make my cursor more visible. Okay, so these orange circles right here are called the input layers. It basically just means that this network right here takes in 5 inputs at the beginning. One of them is the x coordinate of the agent that this is the brain of, the y coordinate of the agent, then tx is the coordinate of the target at that point in time, and ty is the y coordinate, and then angle is the angle of the agent. All of these lines here between the circles or nodes, the circles are called nodes. These just represent that the value in this node, the left-sided hand of the connection. It represents that the value from the left side is passed over that line to the other node it's connected to. And each of these nodes, each of the yellow nodes, multiplies the value it receives by a value called a weight, and then adds another bias to that. That's just a machine learning thing. I'm not going to get into that because it's not really relevant, but it makes sure that the system doesn't get into a deadlock with like values that are 0, input values that are 0, because when you multiply any weight by 0, it will always equal 0. So it does this node, this one yellow node, does that for all of the inputs, and then each of these nodes does the same thing, but with different weights. And the yellow nodes as a whole, they're called hidden layers, or each of these sets of nodes of 3 are hidden layers. And they all do the same thing. All these connections do the same thing, just with different weights. And finally, the blue nodes, after it gets through all the hidden layers, output a single value that is used to decide the action of the car. So the drive thing right here, the blue node that says drive, decides whether or not the car goes forward in that iteration, in the angle that it's pointed. The CW node decides if the car should rotate clockwise, which is why CW stands for clockwise, and then CCW decides if it should rotate counterclockwise. It does this by taking the value between 0 and 1 that's outputted on the node and checking if it's above a certain threshold, and if it's above the threshold, it will do the action. If not, it will not do anything. And you'll see that in the code. When it's deciding, you can see down here at the, I don't know where I put it, but I'll probably think it. So this gets the outputs. Self.brain.think gets the outputs from the neural network. It's right here. I'll go to that later. But in the agent class, it checks if the first output, the drive output, is above this decision threshold, which is right now it's set to 0.5. So if the output is greater than 0.5, it will drive forward. If the second output is greater than 0.5, it'll rotate counterclockwise. Okay, so the diagram is mixed up, but it doesn't matter. If the second output is greater than 0.5, it'll rotate counterclockwise, and if the last one is greater than 0.5, it'll rotate clockwise. So that's how it decides what moves to do. As for the actual mechanics of the neural network, you can see in here how what I just explained in the diagram takes place in code. So in the initializer for the layer class, which is one of these layers, like one of these yellow layers here, or the blue layer, this is the initializer for that. It takes in the number of nodes in that layer, or the number of circles, because this can change. That one architecture that I showed, this architecture is not the only neural network architecture you can do. It's just the one I decided on for this project. Without much thought, I didn't, I kind of just put this in this configuration because it's what I thought of first, honestly. There is a methodology to how you can determine what is best, but I didn't do any of that for this project, just for the demo. But the next input to this class is the input layer. So that should contain a reference to another layer that is the previous one. So say you're initializing this layer right here, this yellow layer, the second yellow layer. The input in the constructor for that one would be the previous one. So it needs a reference to the previous layer, a reference to this layer right here. This is a Boolean to check if it's the last layer, the blue layer. This one is the number of inputs, so the number of nodes in the previous layer. And then this generate here is just a Boolean again to whether or not to generate new weights. And that'll be useful when you're trying to cross over and generate a new set of agents from the previous generation. So this basically, the constructor basically just assigns all this stuff to the class so it can access it in other methods. But it calls in the constructor, it also calls self.generate weights if generate is true, which goes through, it's down here. It goes through and checks if the input layer is none, which if the input layer is none, it means that it's the first hidden layer. And it doesn't need to do this stuff, it'll just do this. But if it is the first input layer, then it will just generate completely random nodes. In right here, you can see with the np.random.rand. np is short for numpy. I imported it up here as np just because it's kind of conventional. And otherwise it will because so this is the shape. The arguments to the rand function is the shape of the array that you want to be generating, the random array you want to generate. np.random.rand will generate a random array with the shape that you pass in here, meaning the number of rows and then the number of columns. So it has the self.num nodes, rows, no matter what. But if it's the first layer, it'll just be the number of inputs into the actual neural network itself. And if it's not the first layer, it will be the number of nodes from the previous layer. So that's just how it's initialized. And right here is how you calculate what values should be outputted from the nodes. So it comes into this layer of yellow nodes. An operation is performed, it's the weight and the bias, like I said before, and then that is the output of this. So this calculates the weight and the bias right here. It checks if it's the first layer again, and if it is, it dots. It does a matrix multiplication with the weights and the inputs. That's just a more concise way of doing that than going through each one and multiplying them individually. It doesn't change the math, it's just formed in a matrix. And if it's the last node, it does something that I'll explain in a minute. But the output itself is just this part, the inner part of this function here. It will multiply the weights by the input that it receives from the previous layer, if it's not the first one. It does this recursively, kind of, as you can see. It multiplies self.weights times the calculate outputs of the previous layer, so it goes back and propagates backwards. This is usually called feeding forward, but I didn't do an iterative method. I did a recursive one, so it kind of is a little backwards, but it does the same exact thing. The only difference with the output layer and the other hidden layers is that the activation function that is called at the end of this. An activation function is just needed to map all the outputs between 0 and 1. It's not actually necessary. You don't really need to do that. It just makes things a lot easier, and it should make the system learn faster. So sigmoid is a logistic function. It's the simplest logistic function. It maps every value to one between 0 and 1 on kind of like an S-shaped curve. If I open up like just a graphing calculator, the sigmoid function is 1 over 1 plus e to the negative x. So this is the curve it maps it to. You see it maps between 0 and 1, all the values. And then there's the one that's used for the last output layer, maps between -1 and 1. But that's just so it can do the decision. Okay, so that's how the neural network works. But neural networks usually use an optimization strategy for their weights to determine the right weights to solve the problem, called gradient descent. But I'm not doing that here, just because it doesn't really make any sense to do that here. This is not a traditional classification task. It's not a classification task at all. And it's not that kind of supervised learning. So I don't use gradient descent. Instead, to determine the optimal weights, or at least better weights, I'm using the genetic algorithm on the neural network itself, which is not my idea. I got this from somebody who I saw doing this on YouTube, and I decided to take the idea and apply it to my own problem. So I guess I'll get into the genetic algorithm now. This is a little more involved than the neural network. So this mostly takes place in the species class, because a genetic algorithm basically models the Darwinian evolution kind of model of species, because you have an initial population, which is the agents at the beginning of the program when you first run it. Then you see how they perform at the task that you want them to optimize for, and you measure their fitness. You measure the fitness of each agent to do the task. So it's a measure of how well they do at the task you give them. So you select the top performing individuals, the top performing agents in that generation, fitness wise, the ones with the highest fitness score, and they pass on their genes pretty much to the next generation. Like you take 2 of the best performing agents, you cross over their characteristics, and then you might add mutation factored in there just because it helps with genetic variation, so you don't get stuck at like brick walls where you can't optimize anymore. Because if there's no genetic variation in this, you can't get new characteristics in the population, so you can't really make any progress. So just to see the selection that I'm doing here, I have two selection functions. This one I could use, but I just wrote this code. Like I just wrote the code for all this project. So like not even that long ago, just the last few days. So this doesn't exactly work right yet, but it's supposed to select the top few agents based on a probability calculated from their fitness score. But this is the one that I'm currently using. It's the one that is actually run when you run the project. It just, this line takes the top half performing ones, the top half performing agents. This is kind of a messy line. I wrote this like probably half an hour ago. It uses a lot of Python built-in functions. So what's going on here is it first generates a sorted array of self.agents, which is the list of agents, all the agents. It sorts them by this function right here, lambda a.calculate fitness. So it sorts them by their fitness and converts that into a list, because sorted doesn't return a list anymore, and I want to index into it, so I need to have a list. And then it does this index. This colon here means this is Python slicing syntax. It will select all the elements up to this index right here, but not including it. So floor just rounds down the number inside of it, which is the length of the current self.agents list. So the number of agents that you have times this keep value, which is passed in as a parameter. And I just let it default to 0.5, which means that you'll keep half of them, because you multiply the number that the number of agents that there are by 1/2, you'll have 1/2 left over in the list. And then I go and reset all of them. Like I reset their positions to the center of the screen. And this also, I mean, it also resets the target to the initial position. So like there's not different conditions every time, because if the conditions change, it's not going to be learning anything. And it just returns these new agents. But that gets passed over to the next generation function, because it's called in here. You can see right here, it says new agents equals self.select pool. That calls that other function with this keep old value. And then it checks how many is kept. And this is the crossover part of it right here. Or, oh no, well, yeah, I mean, it calls the crossover part. So this selects the first parent and the second parent agent that will pass on their genes, and then it generates the child from that. I'll go to the generate child method next, but then it sets the new species to be those new agents. It increments the generation count and sets this equal to 0, but this is not really relevant here. So the generate child method takes in two parent agents and outputs another one that's similar to the two parents. It's a method of the agent class. This is the one that's being called. So it makes a new agent. This is a long line, so I'm probably gonna have to scroll over. It makes this new agent right here, which calls the agent class. It gives it another unique ID. That's just so I can keep track of them. It doesn't serve any functional purpose in the program. But it makes it centered at the original coordinates of its parent on the screen. It gives it the same target, which is the black dot. That's always the same. If this, I could probably structure this code better somehow to make sure that I don't need to actually store this as a instance variable for every single class, or for every single agent that I have. But this was a quick thing, so I didn't really make that happen. But this is the width of the agent. I store it as half size just because I don't want to have to constantly divide by 2 to draw them. So I store it as half size, but I pass it in as full size because the user usually sees that side of it. And then I pass in the same decision threshold, which is the thing that decides whether or not it should move. And then this is the main part of this crossover. Like the main part of this generate child method is it generates a new brain. So it calls basically the neural brains generate child method, which is called from agent and layers. So that is over here in the neural brain, right here. It takes in 2 brains pretty much and outputs another one that's similar. The new brain is, well, this CLS right here is a reference to the neural brain class itself. This is a class method, which means it just doesn't, it's not a method of an instance. It's just a method of the class itself. It's like a static method, except not exactly, because it does contain a reference to the class itself. You can see it with this decorator right here. So it makes a new brain with the same characteristics as the parent, one of the parent brain, the first parent brain. And then it assigns the layers to that new brain and returns it. So as you can see over here in the agent class, I'm passing in as the layers argument self.brain.generate child layers. So that is down here, generate child layers, which calls the crossover method of these. So down here, what's actually going on, this is where the actual crossover of genes happens. So this is like the main part of the genetic algorithm. I'm just looking at this because I kind of, okay, so it generates a new empty matrix of zeros. The zeros don't matter. They're just placeholder values so I can get the right shape of array. Zeros like, np.zeros like generates a it generates an array of zeros in the same shape as the array you pass in here. So I want a new array the same shape as the weights of this brain. Then I iterate over the array and I do this processing on it. So this is how I was doing it before, but it didn't really work. I was averaging the 2 weight values and assigning it to the new one. But I figured that would kind of cause a drift towards like everything would drift towards 0.5 because the weights go, well, I mean, everything would drift towards 0 or 0.5 because just because of the range. If you keep averaging them over and over, they're going to tend towards that value. That doesn't really work. I commented that out. I should probably just delete it. But the new thing I do is take a random value. If it's less than 0.5, I assign the new weights at this index to the current agent, the current layers weights at that same index. Otherwise, I assign the new index, the new weight to the other parent layer weight. And then after that, this is the mutation I was talking about. If the random value, np.random.random returns a random value between 0 and 1. If it's less than the mutation chance, which is up here, it's an argument, it will call this code, which has a 50% chance of multiplying the weight that was just generated up here by 1 plus the mutation magnitude. So that's the maximum size, like maximum multiplier that you can have for the mutation. Otherwise, it multiplies the thing by, or the new weight by 1 minus the mutation magnitude. Then it just returns a new layer with these weights. That just calls this method. It doesn't really have any functionality other than just making a new layer with the specified weights that you provide. Okay, so I've kind of just covered a lot of stuff kind of quickly. So does anyone have any questions right now so far about what I've talked about? Because I can, if something wasn't clear, I can try to clear it up. I can't really see that. Okay, so if no one has any questions, then I guess I'll just keep going.
Chat.
Oh, sorry. What was that?
I was saying, so far nothing in the chat, so looks like you're clear. You're doing great.
Okay, I can't see the chat.
You see the link down at the bottom.
All right, so I guess I'll just go on here. Okay. Oops. Yeah. All right. So I just talked about the crossover. So that is what is going on over here when it's generating the next generation. So basically that means it keeps half of the old generation, the best performing agents from that generation, and it generates the same amount of new children from the previous generation. So that's where mutations occur and new behavior can come from. Okay, so back to the main file right here. Wait, oh no, never mind. I already talked about that. I think that's actually everything. I think I'm done. Unless anyone has questions. I might have forgotten something. Oh, well. Oh, no. Yeah, I did forget something. Okay, so, okay, these are just helper functions, not what I was going to talk about. So, scikit-learn is a library in Python that I actually don't have installed on this computer because this is not my normal computer that I use. But scikit-learn is a machine learning library that will make a lot of these things that I hard-coded a lot easier to do. And I think I'll just talk about quickly the basic things in that library that will help you do this a lot easier. I'm not the most familiar with the library, but I know what it is. I looked at it. I considered using it for this, but I figured it would be more useful to implement it myself so you could see how the inner workings of it. Like compute the optimized weights. Let me just, I gotta install scikit-learn so I can import it. But the scikit-learn library contains a class called MLP classifier. MLP stands for multi-layer perceptron. That's just a fancy name for a basic neural network like this one that I was showing before. This is a multi-layer perceptron. It's typically used for classification tasks. I'm probably abusing it a little bit actually by using it for this non-classification task. But I've seen a lot of people do it, so I know I'm not the only one. But basically you can like call the MLP classifier class and do the same exact things that my neural brain class does. This class right here, it does pretty much the same thing, except probably more efficiently because I'm not sure if it's implemented in Python or not, but it's probably implemented in a faster language that has bindings. I'm not entirely sure about that, but if I had to guess, that would be it. I am just trying to find this thing here. Okay. I don't know. I guess I won't. I guess I don't need to install it.
Looks like in your path, maybe it was the username that you had users/s.
Oh yeah, that was the correct thing. I just
okay.
Yeah, I just I installed a different version of Python than I usually use. So uh, actually, I installed a different version of Python that I usually use. So it's not, this is not going to be the correct path. But I just figure I could go in here and change this directory and figure out what the correct one is.
If you go to the end of that and hit tab, or there you go. That works.
Oh, I was just gonna.
That works too.
Okay, so it's. I called this. Oh, I'm in the Python thing. Okay, so. Okay, so they must have changed that. Oops. Forgot to type CD. Okay. Yep. Okay. Okay, I don't know what I'm thinking with.
There you go.
All right. So this should install scikit-learn. I've had problems with this before, so if it doesn't work, I'll just not try to debug it anymore because I know this is not entertaining at all or good to watch. But okay, so the MLP classifier. This is the documentation for it. So as you can see here, it has a lot of the same things that my neural brain class has. It's in the sklearn, which is scikit-learn, neural network.mlp classifier class. So the hidden layer size here, that's the same in function as my argument over here that has nodes per HL, nodes per hidden layer. That's the same argument, it looks like. And activation, that's what I talked about before, these things. These are the activation functions. It defaults to ReLU, which is a different kind, neither of the ones that I was using. This is I don't really remember what that is. This is probably the learning rate. So typically in gradient descent, you'd multiply the gradient of a cost function by this value to optimize for the best weights, but I'm not doing that because this is, again, it's called MLP classifier. It's supposed to classify data, like sort it into groups, pretty much. Learning rate characteristics, yeah, this is a bunch of stuff that I don't have. So this is like the one I have, except it just has a lot of more features and it's designed for classifying. But you could theoretically use this exact class and just implement the genetic algorithm aspect of it, because as far as I could find, there was no nothing in scikit-learn to actually help with that, although I'm sure there's some Python library. If you want to do anything, there's always a Python library for it. That's just kind of how things go with it. But if I'm wrong about this, if scikit-learn has a class or a useful function for genetic algorithms, somebody can tell me that, but if you know, but I don't think it does. So yeah, you could just basically just not call the optimize function on this MLP classifier, and then take the outputs from it and use it to change the weights. That probably wouldn't be the best practice, but this could definitely be used to make it easier, because it took most of the time I spent on this class or on this project was probably about 2 days, because I started it yesterday. Yeah, so I started it yesterday. I did most of it yesterday. But it took me like 2 hours just to do the neural brain in the layer class, which is the MLP classifier's role in this. But yeah, it kind of ports pretty easily from this hard-coded solution to that scikit-learn one. And again, this is just a demo project. Like, this obviously is not useful for any real world problem, but the point is that it demonstrates the concept of learning. Okay, so I kind of lost my directory here, but you can use this algorithm for all kinds of other things. Like I've seen people use it for like Mario games, old Mario games. They'd hook up a neural network with a genetic algorithm on there, and the thing would learn how to play Mario. That would require more advanced system than what I have, but it's the same principles. Like these just generalized to more complicated problems. And I think that is everything I have for now. So if anyone has questions, I'm happy to answer them. But if not, I think that's all. I'm just trying to do the demo again. I probably should have had this running the whole time so you could see. Eventually it does chase the thing around in circles pretty well. Like it pretty immediately figures out that it should be going in the clockwise direction, but beyond that it doesn't really get too far. Like that one pink car that's driving pretty closely to it kind of figured it out. So that means that the ones that are driving closest to the black dot will be like on average the closest to the black dot, they will be kept. And then the ones that are kind of like stagnant over here, just kind of running into the wall, like the initial generations were, they're killed and not kept. They don't get to like have any impact on the next generation. So the one problem that I kind of have here is that in the center where all the things start, it will be at most, if they don't move, it'll be at most the radius of this circle away from the thing at all times. So it's already better than the ones that just fly into the wall. But you can see that it is trending towards, these cars are driving generally towards the dot. Oh, and I forgot to show the fitness function itself. So over in here, there is in the agent class, there's a function that says calculate fitness. So the idea is that the highest fitness agents will be passed on. So this, the agents want this number to be high. So it'll do the total distance divided by the iteration count. So how many iterations they were alive for. So that just gives the average distance away from the target, and does 1 minus that value, because you want the larger values to be you want the larger values to mean that it did well. And since I have the coordinates of each mover, of each agent normalized between 0 and 1, this value will always be between 0 and 1 as well, so it'll never go below 0. But I could put other things in here. So this calculate fitness function only optimizes for distance from the target, only distance from the black dot here. And I could put other things in there, like I could have it also take in the distance from each other. So like theoretically they'd fly in a flock and not overlap with each other if you had a bunch of generations. But this typically takes a lot of generations to really do well. Like, and when I'm drawing all the generations and actually having it take time to do all this stuff, there's not really a way I could sit here and have it train the whole time. That would take too long. But this, as I said, this is open source. So if you go to this GitHub repository right here. It's sam-lb/car.ai, or you can just go to my profile and click on the repositories. My profile is sam-lb. You go to the repositories. It's the most recent one right now. So car.ai, it's the same thing. And likely I'll pretty soon be putting up an interactive version of this where you can just go to the internet and like train your own things if you want to. That'll be over here. It's on my website, sambrunacini.com/games and interactive content, but you can just go to sambrunacini.com and hit the apps and games. It'll scroll down here. It'll be one of these things. It's not up yet, but that'll be running, and that won't be in Python. It'll be with JavaScript, but that doesn't matter because the code for that other one is over here. You can just hit the download button on that, or fork it, or whatever you want to do. Okay, so I'm definitely done this time. I don't have anything else to cover. So any questions I can answer now.
I had a question.
Okay.
Yeah, this is Ken. When you're training this software, you can run it without the GUI running, right? I would imagine to speed things up.
I mean, most machine learning implementations do that, but I just made this, so I didn't really have enough time to make a way to do that. So yeah, in the future, or like traditionally, that would be something to be included. It makes a lot of sense to do that because it won't take as long to train. You don't need to go through every iteration and draw the stuff over and over. But yeah, in my project right now, no, you can't do that yet.
Okay, and then this is probably more of a machine learning technique. Is if you tweak some of your parameters, technically your data isn't correct anymore. But the people just tend to start with that trained data, even though they've tweaked some of the parameters.
I'm not sure what you mean.
So you say you've taken hours to generate some data.
Oh yeah.
Well, but then you change the way it works in some respect. Instead of starting at zero.
Yeah, not yet. Again, I could. That is something I could put in, but
the I guess the way the field works, or the way the industry works.
Yeah, typically you could make some way to like save the weights of your model. And I'm sure that the MLP classifier from scikit-learn has some way to do that. Like you could save it in a file somewhere, but I don't have that yet. Another thing you could do is like seed the random generator to make sure that you get the same results as you got on a previous run. So I'm not sure what the NumPy random function is, but it's probably something like np.random.seed, and then you just put in a thing there, and that number doesn't really matter as long as it's the same every time you run it, and it'll be the you'll get the same results every time. You'll get the same random numbers because, after all, the number generator is not actual randomness; it's YASI. So this tells you pretty much what I just said. You can see the generator and get the same results every time.
How many iterations have you run this solution?
Not that many actually. The most I've done is like probably 10 or so, because I haven't tested this out a whole lot.
Okay. I thought you were going to say like 1 million.
Yeah, well, I mean, yeah, definitely when I get rid of the necessity of the GUI part of it, I'll definitely crank that up a little bit and have something like 1 million or 100,000 iterations running on this thing. And by then, if it doesn't chase around the dot, I'm pretty sure there's a problem, but we'll see.
Yep. Okay, thank you.
Any other questions?
All right. Well, that was fabulous, Sam. Thank you very much.
Thank you.
And I like that you took the time to do things out manually to really demonstrate how everything fits together.
Yeah. I mean, for practical implementation, it's probably not the best idea to do things yourself, since people have like optimized this over a long period of time. But you know, just for the purposes of demonstration, it's definitely good to see how the inner workings of machine learning models work. So, because you don't want to just treat library calls like black boxes, because that can lead to a lot of problems.
Yeah, no, it definitely helps to know what it is that you're leveraging.
Yeah.
Cool.
All right.
All right. Well, if nobody has anything, I will sign off and say thank you, Sam, and we will get this recording up, and I'll link to Sam's GitHub from the video.